So let's solve a heat exchanger design problem, or in other words, let's design a heat exchanger. Okay, so let's say example. A counter current flow heat exchanger with a heat transfer area of 12.5 meters squared is used to cool oil with a CP hot of equal to 2000 joules per kilogram centigrade, with water, which has a CP cold of 4170 joules per kilogram centigrade. The oil enters at a temperature of 100 degrees centigrade and at a flow rate of 2 kilograms per second, while water enters at 20 degrees centigrade and 0.48 kilogram per second and a flow rate of 0.48 kilogram per second. The overall heat transfer coefficient is 400 watts per meter square centigrade. So calculate the exit temperature of the water. So this is not a sizing problem, this is a rating problem. So there is already an existing heat exchanger and you want to see whether it's going to be useful for your purpose, or you want to see what is going to be the exit temperature for this arrangement. Okay. Solution. Okay, I think it's a good idea to draw a schematics. It always helps. You have a pipe. I guess it's better to let the hot inside the inner tube. So the oil in, oil out. This is hot oil in. And then you have outside water flowing in the other direction. Cold water in, water out. Okay, so that's the arrangement. What do I know? I know the inlet temperatures, and I don't know the outlet temperatures. So I'm not going to be able to calculate the log mean temperature difference. So that method will involve iterations. So you can write down using log mean temperature differences method would involve iterations, and thus we will commit to the number of transfer units method for solving for T cold 2, right? That's the water exit. So in NTU method, we calculate the heat capacities, mass times heat capacities, and compare them and find the minimum of them, and then we calculate the number of transfer units, right? So we first calculate MH, CPH, and M cold, CP cold, and then find the minimum of them, right? The MH, the hot flow rate, is the oil flow rate, right? What is the oil flow rate? It's 2 kilograms per second. CP hot is the hot side heat capacity. It's the oil heat capacity. It's 2000 given. 2000 joules per kilogram centigrade. That's equal to 4,000 watt per centigrade, or watt per Kelvin, doesn't matter. Either way is fine. Joules per second is watts, so you can either write joules per second or watts instead. The mass flow rate of the cold stream is the water flow rate, which is 0.48 kilograms per second, and the CP of water is 4,170 joules per kilogram centigrade, and you should get, what you get, I guess 2001.6 watt per centigrade degrees Celsius. Okay, so far so good. Now we're going to calculate the number of transfer units, right? Which we are going to use to calculate the epsilon. So let's first write down the formula for the number of transfer units. From our notes, we know that we declared NTU to be UA over C minimum. And C minimum is the minimum of these two numbers. And the U is given as 400 watts per meter squared centigrade. And the area is given 12.5 meters squared divided by Cmin is the minimum of these two, which is basically this one, 2001.6 watt per degree centigrade. Okay, from here you should get something like 2.498. Okay, and now you can calculate the epsilon, which without actually needing any temperature values, right? Because the epsilon is for the counter current. We should go back to your notes or the book, actually page 378. For counter current flow, the epsilon is 1 minus exponential minus number of transfer units, 1 minus C min divided by C max divided by 1 plus that's 1 minus C min over C max minus number of transfer units. I'm sorry, that's exponential. No, it's not exponential. I'm sorry. I'm sorry. Yeah, that's exponential. Yeah. Exponential minus number of transfer units, 1 minus C min over C max. Yeah, let's check. Yes, this should be correct. Let's check our notes as well to make sure we are consistent. Yeah. So this one. $378. Okay, good. So that's the formula. So let's go to lecture 15. Okay, good. So we're going to plug in the numbers. So epsilon is equal to 1 minus exponential. Number of transfer units is 2.98, negative 2.98, sorry, 2.498, 498 times 1 minus, the Cmin is 2000 and 1.6 divided by Cmax is 4000. So these two units cancel, so I don't need to write down the units of them. So this one is unitless actually, and you're going to see that this one is also unitless. See, if you check this thing, the watts cancel, right? Centigrades cancel, meters squared cancel. This is unitless. Okay, so everything within this exponential is unitless as expected. I mean, exponential, the arguments of exponential must be unitless always, no matter what formula you have. Divided by 1 minus Cmin over Cmax, 2001.6 divided by 4000 exponential minus 2.498 times 1 minus 2001.6 divided by 4000. Okay. And from here, let's find epsilon is equal to 1 minus, let's calculate this exponential first. Can somebody calculate it? I guess I have like wrong numbers in my notes, so that's why I want to calculate this thing again. So let me use Google Calculator. Okay. 1 minus 2001.6 by 4000. Okay. Times 2.498. Okay. Exponential. Okay. Okay, there you go. So this must be 0.287 divided by 1 minus 0.287. Okay, so let's calculate this too. .713 divided by 0.56. So this gives us 0.833. Okay, so we found the epsilon. Okay, so the good thing about finding the epsilon is now you have an equation that relates to temperatures. Let's go back to our previous lecture and go back to the original definition of epsilon. Okay. Yeah. The effectiveness, which is the delta T of the fluid with the lower total heat capacity divided by maximum possible temperature change in the system. Okay. So I guess there's a, okay, here you go. The Q actual divided by Q max. Okay. So basically you can calculate the Q max and find the Q actual if you like. So whichever way you wanna do this. Or you can just say it's the TC2 minus TC1. Let's see, for our case, which one has a lower heat capacity? Let's see, let's figure it out. There you go. Okay, so MCPC is smaller than the MCP hot. Okay, so given that MCPC is smaller, so this means that you should commit to this formula, which gives you this. So we're going to have the epsilon equal to TC2 minus TC1 divided by T hot 1 minus TC1. Okay, so we're going to write it. That's right. Since MCCPC is smaller than M hot CP hot, epsilon must be equal to TC2 minus TC1 divided by T hot 1 minus TC1. Okay. And given the numbers, epsilon is 0.833. TC2, we don't know, right? Minus TC1 is the water inlet temperature, right? Let's see, where is that? Yeah, the water inlet temperature is 20 degrees centigrade divided by T hot 1. T hot 1 is 100, right? The oil enters at 100 degrees centigrade. 100 degrees centigrade minus TC1, which is 20 degrees centigrade. Okay. And what do we find from here? TC2 is equal to, let's do it, times 80 plus 20. So we get 86.6 degrees centigrade. So that's the water outlet temperature. Okay. Do you have any questions so far? Okay. From here, you can even calculate the heat duty if you like. And You can calculate the log mean temperature difference and to check your answer whether that's correct. So you can, I mean, you can do that. You can use the log mean temperature difference method just to check your answer whether this number is correct. So you can actually calculate the LMTD using the given temperatures or the salt numbers.